right, everybody, we're going to try one more video. We did talk about in the earlier video just the immediate E1 reaction. I want to go over a little bit of a more complicated system. So first we're going to talk about the idea of beta hydrogens. So if I'm looking, boom, 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 and I'm going to put my bromine here, and boom, boom, sorry. So hopefully you can see the compound that I made. What I'm going to do in pink, or do I have a different color? I guess I'll use this light blue, is I'm going to identify my beta hydrogens. These are my beta hydrogens to that carbon. These are the beta hydrogens. 1, 2, and this is a beta hydrogen. So all of these could be taken off once I make that carbocation. And we're going to talk about which product is favored and which is not. So the first thing we're going to do as our E1 reaction, and this time I'm going to use sodium bicarbonate, NaHCO3, not a strong base, not a good nucleophile. It will only be a base once we get to the carbocations. Totally dependent on my bromine coming off, and boom, boom, methyl here, boom, boom. And now I have a plus charge here. So now, you see how many different colors I have. I have these 3 beta. I have this 1 beta. And if I can find my pink marker, I can show you my other beta. Oh, I have a brown instead. And I have these 2 brown. Those are the only places I can remove a beta hydrogen from, because I'm not removing it once I get past that beta point. That is not acidic. Remember, these hydrogens on this compound at this stage, not very acidic. Once they get to this point with the cation, they become acidic, and acidic enough so that even bicarbonate can take them off. So what we're going to do is we're going to look at each of the 3 scenarios to see what our products would be. Let's first take the green scenario. The green scenario, the base comes in, takes off this hydrogen, and puts it, and we make that the alkene where my carbocation was. 1, 2. I can have this, or, right, this one would be Entgegen, or I could also do the cis version where both my methyls are pointing the same way and both my ethyls are pointing the same way. For this methyl group, I can take off any one of these hydrogens. It will basically be the same thing. The base comes in, boom, boom, and I get double bond. Okay. For hydrogens. We'll do it on this side. And the base comes in, and hopefully, I believe you can see the whole screen. Let me check. Yep, you can. Yay, okay. The base comes in, pulls off the hydrogen, we form a double bond. Boom, 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 boom. Now I have a double bond, and I can either be E, or I could be Z. And that would mean 1, 2. There you go. So I have a possibility of 5 different products. We already know that E is more stable than Z, right? E is more stable than Z. Now we're going to look at substitution on our hydrogens. So if I look, and I look across the double bond, I have 4 different carbons attached to each of these sp2 carbons. So if I look at the 2 carbons in the double bond, I call this tetrasubstituted. Because each carbon has 2 carbons, organic pieces attached. This one, if I look at these 2 carbons, I have 1, 2, and then I only have hydrogens here. So this one is disubstituted because each of those hydrogens takes away one of those substitution pieces. 2, Ted. And if I look at the brown, and I look at the 2 carbons involved in the alkene, I see I have CH3, this organic, and a hydrogen here. So I don't count the hydrogen in my substitution, I am trisubstituted. Substituted. Okay? And the general rule is the more substituted you are, the more stable the alkene. So that would mean this would be the most stable, so this would be number 1 in stability. Then the E, and then the Z form, second. Then we would go and look at our tri-substituted. And this would be number 3, and this would be number 4. That monosubstituted would be the least stable. So we'll talk about the implications and how to predict and how to kind of control this using energy, right? It's easiest to pull off these because they're the least sterically hindered, but this gives us the most stable product. And remember, I think it was a week ago when we talked about thermodynamic versus kinetic product. This might be a kinetic product. These would be your thermodynamic. I'm going to stop there and we will pick up and we'll start with our elimination reactions on Friday or next class.